We defined work last week as the change in energy experienced by something. Now, can you tell me what two things are required in order to change the energy of something? What two requirements do we have for something to gain or to lose energy? We need a force. Yeah, you got to apply a force to change energy of something. This desk is sitting at rest right now. It's not going to do anything. It's not going to gain or lose energy if you don't apply a force on it. We need a force. What else do we need to change the energy of that desk? We need movement. We need displacement. I can apply a force all I want on this desk. Maybe that force just simply deforms the desk, changes the shape of the desk, because we know that forces can do that, right? It can accelerate an object or deform the object, change the shape of the object. That's not good enough. We're not doing any work on an object if we just simply deform it. We have to actually move it because we're not changing the energy if we simply deform it. We have to actually cause it to move in order to have it gain or lose energy. Question? Okay, yeah, we'll get to that in just a second, but you're right. Now, because work is dependent upon force and displacement, we usually just write down the equation as, sometimes we can make it delta E, but we usually just write it down as F times D. But sometimes F times D doesn't work. When doesn't it work, Laura? Yeah, yeah. In other words, if you're pushing it at one angle and it moves at another angle, F and D in this equation must be parallel to each other. And most times in a question, the force is parallel to the displacement, but sometimes it's not. If it's not parallel, then what we got to do is effectively find the X component of the force. In other words, the component of the force that is parallel to the direction of motion. Let me give you a few scenarios here. Tell me what theta is for those different scenarios. By the way, in order to get the x component, easiest way is just tack on a cos theta on the end of the equation. Usually f times d, but then sometimes we have to make it fd cos theta if theta isn't zero. The angle between the way that it's pushed and the way that it moves isn't zero. All right, let's give you a couple scenarios here. Let's say that we push it to the right and it moves to the right. What's theta in that case? Zero. What's cos theta? What's cos zero? 1. F times D times 1 is just F times D. So we could drop the cos theta in that case, right? Let's say we push it to the right and it moves to the left. What's theta in that case? 180. What's cosine 180? It's negative 1. So you got F times D times negative 1. So you get the same value as you got right here, except you end up getting a negative value for work. What does that mean? Work's a scalar. There's no direction associated with it. A negative work doesn't mean it's to the left. A negative work means that you've lost energy. And if you think about that, it should make sense, right? If it's moving, something's moving to the right, but I push on it to the left, then I'm taking energy away from it, right? I'm slowing it down. I'm taking energy away. Therefore, it should be a negative work, a negative change in energy or a loss of energy. What if I apply a force this way and it moves this way? What's theta then? 90. What's cosine 90? What's cosine 90? No, 0. Cosine 90 is 0. So if we have F times D times 0, what's the work done? 0, because there is no component of that force that's parallel to the direction of motion of the object. What about this one? We did this. We did an example like this on Thursday, but we'll go through another one here. Let's say we've got an angle of 10 degrees right here. That's the incline, but I'm pulling it at an angle of 40 degrees right here. It moves up the incline. What's the theta that I'd use now? Not 30. Sorry, not 50. What is it, Isaiah? It's 30, right? 10 degrees is the way that it's moving. 40 degrees is the way that it's pulled. I don't care which way it's moving or which way it's pulled. I care about which way it's pulled relative to which way it's moving. So the difference in that angle is 30 degrees. The angle between the way that it moves and the way that it's pulled is 30 degrees. That's what I care about. Yeah. So it would be F times D times cosine 30 degrees in that case. That make sense? All right, let's take a look at the 4 questions that we had for homework now then. Page 294. Which ones of those 4 would you like to go over here? Probably question 4 for sure. What about 1, 2, 3? Yeah, we can. We can go over those. Yeah. Are we okay with number 1? Okay, number 2, 3, and 4 it is. Number 2 says a force acts at an angle of 30 degrees relative to the direction of the displacement. What force is required to do this much work over a displacement of 25 meters? Clearly, it's a work question, and we have an angle there between the way that it moves and the way that it's pushed. So we have to include that. That means that we have to use our equation F times D times cosine theta as opposed to just F times D. If theta is 0, then FD works. If theta isn't 0, then it becomes FD cosine theta. What are we looking for? Looking for force. We're going to say it's W over. How do you take the D over? Dividing? How do you take theta, cos theta over? If we're trying to solve for theta, just theta, we'd use the inverse cosine. But if you're taking cosine theta over, take the whole term over, you can take it over just the way you do any other term. You're going to divide. So it becomes F is equal to W over delta D times cosine theta. We're going to say W is 9,600 divided by delta D, which is 25, times cosine 30 degrees. Now let's pull out the calculator to do this one. Let's say 9,600. And watch how I use brackets here. Put in brackets, everything in the bottom in brackets, 25 times cosine 30. But look what the calculator does. It introduces another bracket with the 30 degrees, right? So we have to end that bracket, and then we have to end the first bracket that we have. We end up getting 443. To 3 significant digits, my force is 443 newtons. Is that okay? Nick, is that okay? You got that one? All right. 3 says a force of 640 newtons does 12,500 joules of work over a displacement of 24. What's the angle between the force and the displacement? This one's a little bit tougher to rearrange for, right? There is an angle, so we're using FD cosine theta. We're talking about work here, so clearly it's a work problem. Got to solve for theta. What I want you to do first is solve for cosine theta. Take the F and D over by dividing. Cosine theta is equal to W over F times D. Agree? How do you solve for theta now? You can't just take the cosine over by dividing and be left with theta. How do you solve for theta? You have to do inverse or second function cosine. So theta becomes second function or inverse cosine of W over F times D. Right? We'd like to take the cosine over by dividing, right? Theta is equal to W over FD cos. But it doesn't work that way with a trig function. Unless you're taking the whole thing over, you can't just divide it. You have to take the inverse, the second function of it. All right, so what do we got here? Cosine, the inverse cosine of work, which is 12,500 over F times D, 640 times 24. Okay, let's do that on our calculators. Second function, cos, right, see what I did there? Second function, cosine, that's the inverse cos. 12,500 divided by bracket, 640 times 24. Then what? And the bracket, and then what? And the other bracket, because we had 2 open brackets, we have to have 2 closed brackets. We end up getting 35.5. degrees. All right. That's probably a little bit trickier. Hey, number 3, I'd say. Question number 2. Yeah, because of the coast of the -1 for sure. Okay, number 4. A bungee jumper with a mass of 60 kilograms leaps off a bridge. He's in free fall for a distance of 20 meters before the cord begins to stretch. How much work does the force of gravity do on the jumper before the cord begins to stretch? Again, it's a work problem, right? How much work does gravity do? It's a work problem. Why am I writing down the equation this time as just F times D as opposed to FD cosine theta? Yep, Jack. Yeah, exactly. Force and displacement are in the same direction. If it moves downward, it's because there's a downward force. There really is an angle, but what is the angle? Not 90. 0. Yeah, 0 degrees. And cosine 0 is 1. So we can just drop it. What's the force? M times G. Right? The force is M times G. So it becomes M times G times delta D. In fact, some of you probably solved this question not using F times D, but some of you probably just found the potential energy, MGH. Well, potential energy, it's not, the answer isn't really the potential energy. The answer is really the change in energy, right? But because the final is 0, then it ends up being the same thing, right? It's just the initial potential energy. Well, I'm solving it using F times D. But look what happens when I say F times D. M times G times delta D is same as the height. So it becomes essentially MGH, which is the potential energy. Okay, our mass here is 60 kilograms times 9.81. Don't just make it 60, because that's just mass, not force of gravity. 60 times 9.81 times the displacement of 20 meters. By rights, we should have negative in here, because the force of gravity is downward and the displacement is downward. But in a case like this, it might make sense to define down as positive. Doesn't really matter. We get the same answer either way. We do the math here, whether we make them negative or positive, we end up getting positive 1.18 times 10 to the 4 joules. This is how much work gravity does on this object. Make sense? Yeah, you could do that. 1.18 or 11.8 kilojoules. Yeah. Question, if you didn't hear that, was could we also write it as 11.8 kilojoules? Yes, you could. Okay, that's we don't see that one very often. Usually we see either standard or scientific notation for the base units, but it's absolutely right to do that. Yeah. Questions on this? All right, we've got two more examples that I would like to do here. The first one is much like questions you've already done here. The second one is a little bit more to it here. These ones, unfortunately, are not in your textbooks, so you're either going to have to copy these or snap a photo of it. First one says a 20 kilogram object gains 300 joules of kinetic energy as it's pushed a distance of 100 meters. Calculate the force used to push the object. This is almost the same as questions that you've just done. What's different about it? I don't see the word work in here anywhere. This is a work question, however, even though I don't see the word work in the question at all. What in this question tells you that you've got a work question? Yep, Max. Gain of energy, right? That's a change in energy. And what's a change of energy defined as? Work. So even though we don't tell you you have this much work in so many words, we do tell you in this question that you've done this much work. Okay. We could rephrase this, say a 20 kilogram object has 300 joules of work done on it. It gains 300 joules. It's 300 joules of work done on it. What's the force used? Well, now it becomes a problem just like the other ones we've done, right? Mass is 20 kilograms. We've got our work, we're going to call it now, is 300 joules. We've got our displacement of 100 meters. And we're looking for the force here. So we're going to say work is equal to F times D. We don't have an angle given to us, so we have to assume that it's being pushed in the same way that it moves. Let's rearrange this to solve for force. We get W over displacement. We get 300 joules, 300 joules over 100 meters, which is 3.00 newtons. Is that right? Notice I didn't use the mass in here at all. Is that intuitive or counterintuitive to you to not use the mass here? A little bit counterintuitive, I think. Yeah, I think it is a little bit counterintuitive. Although some of you might get that right away, why the mass isn't important. Here's the thing. You apply a force on this object of 3 newtons. And you apply a 3 Newton force over a distance of 100 meters. It doesn't matter what object you're pushing. If you apply a 3 Newton force for 100 meters, your effort is the same. You push this 20 kilogram object, you push a 10 kilogram object with a force of 3 newtons, your effort is the same, right? That means the amount of work that you do is going to be the same regardless of which object you're pushing. Now, the 10 kilogram object would accelerate quicker with the same force. It would end up going faster than the 20 kilogram object. But the work that you did on it, the effort that you expended on it, would be exactly the same. That make sense? Okay, I got one more for you, and then I'm going to set you to work on a few questions yourselves. A 1,200 kilogram car accelerates from rest to 90 over a distance of 200 meters. What's the work required to do this? How much net force is required to do this? I'm going to circle this. How come? I don't want kilometers per hour. I want meters per second. So I'm going to have to convert that to meters per second. We know that this is a work problem. We know we got to find two things, but clearly work is part of it. Let's write down some givens now. My mass is 1,200 kilograms. VI is 0 because it starts at rest. VF is 90 kilometers per hour, which, convert that to meters per second, 90 times 1,000 divided by 3,600. I think it gives me 25 meters per second. My displacement is 200 meters. We want to find the work done, and we want to find the force. All right, so what do you want to do first? Force or work? Force. That's fine. I'm going to do this. I'm going to set that up at least in green. Okay. Okay. Solving for force, I would probably say m times a, right? And then I would say for a, probably vf squared is equal to vi squared plus 2ad. Vi is 0, so a becomes equal to vf squared over 2 times d. So we got, what do I get? 25 squared over 2 times 200. What do we get there? 25 squared is 625 divided by 400. 1.5625. And now we're going to say 1,200 kilograms times 1.5625. $18.75. We're going to round that to 2 digits, right? 1.9 times 10 to the 3. And then, of course, work is equal to F times displacement, which is 1875 times 200. What is that? 375,000? 3.8 times 10 to the 4. Make sense? That's not the way I do it. That's fine. Nothing wrong with that at all. That's not the way I was going to do it. How was I going to do it? You tell me how I was going to do it. No. No, it wasn't going to be to find time. Did you find time and then found acceleration? Okay, that's fine. Here's what I was going to do. I was going to say W is equal to delta E, because work is change in energy, right? Well, delta E is final minus initial. The final energy is kinetic. The initial energy is zero because it's at rest, right? So I can say now W is equal to 1/2 of 1200 times 25 squared. And when I do that, guess what I get? And then I was going to say W is equal to F times D, or F is equal to W over displacement, which is 375,000 divided by displacement of 200 meters, which is 1.9 times 10 to the 3 newtons. Which way is better? I don't think there is a better way. I think they're both good ways of solving this question. Okay? Just to point out that A, there are different ways of solving it, and B, if you solve it in two legitimate ways, you have to get the same answer either way. Yep, Jack? Right here? I just said W is equal to delta E. That's the change in energy, because that's how we define work, right? Is a change in energy. But then I said, well, change in energy is going to be final minus initial energy. What's the final energy here? Kinetic energy, because it's moving, right? What's the initial energy? Zero, because it's sitting there. Make sense? So it becomes 1 FMV squared minus initial, which is zero, and then good. Or you could have, or I say yes, you could have found time. Yes, and gone from there. All right, now I'd like you to work on your third worksheet in that booklet that I posted in Google Classroom here the other day. I'll also put it up on the board for you as well. That third worksheet is your work worksheet, or as I sometimes like to call it, my work squared sheet. I'd like you to do questions number 1 to 7 on your work squared sheet, please.